about braking on ice. Doesn't matter that you have a big brake. No. Why? You cannot put it to the ground. I think the most worthy upgrade is tire, actually. Tire quality, man. People underestimate that so much. But before we talk about tires, by the way, we haven't talked about tires. I forgot to put it on my list of topics. Braking distance. So your braking distance depends on this contact. So, as long as your brake is able to lock the wheel and skid your car, basically lock the wheel and it's screeching halt, okay? Then the brake is good. And brakes are designed to do that. Even cars with very cheap cars, even very cheap cars, very small cars like Daihatsu Ayla or Toyota Agya, right? Honda Brio. Their brakes look small, but it's good enough to lock your wheels. And if your brake is good enough to lock your wheel, the big brake upgrade will not reduce the brake distance because the limitation or the bottleneck of your braking distance is your contact. Okay? But, like you said, when will that be relevant? When will big brakes make a difference?
So usually, if you are going for big brake kit, usually you need more frequent braking.
Okay.
So,
what does more frequent braking does to your car and brake systems and brake performance?
Heat generation.
Heat generation, right? Think about the heat. I have an animation on this.
Okay, so 2 weeks ago I made this.
There's a controversy.
High speeds. That's so necessary is if you dramatically increase the mass of engines as well as possible. The reality, whether this is something you need to do from a function perspective, is an entirely different matter. In reality, significant brake upgrades would likely end up very much near the bottom of the list of wants and a negative attitude to.
Okay. Think about your heat in your brake like a bucket of water. Okay. So this is the heat capacity of your brake system. Okay, and then this is the amount of heat is the amount of water in your bucket. Okay, in your canister. Every time you brake, you're increasing heat, right? So you're pouring water into it. So you're increasing the heat. Increasing the heat. Every time you brake, you put in water into the bucket. At one point, it's gonna overflow, and that's when your brake pad stops working because your material starts to melt and all that. But there is something that helps you, right? You got the heat transfer out. So you got, every time you brake, you put water in, and every time you, well, not every time, but all the time, there is an opening. This is the heat out to the environment. Okay? So braking is about heat in or heat generated and heat going out. So every time you brake, maybe you got that much volume, and then this volume gonna dissipate, right? And then you brake again, you put in more water again, and then it dissipates. Now, what does a big brake kit do to this bucket? Gives you a bigger bucket, that's what it is. Okay, a big brake kit, basically bigger rotor, more mass, it's just a bigger bucket. Okay, I would argue that actually upgrading the piston will not make a difference compared to enlarging the rotor. Because enlarging the rotor, you have a bigger bucket. The amount of heat that can be contained by a bigger rotor is bigger bucket. So you can brake more often even though you didn't have the time to dissipate the heat into the environment. Okay? So the limitation is here. The bucket and how much heat you can get out to prevent the water from overflowing. And so that's the essence of braking, is heat transfer. There is one more discussion on this, which is the...
Hello everyone and welcome. In this video we're going to be talking about performance rotors, drilled, vented, and slotted, and...
So, this is also
why you
a debate, right?
each of these individual features. Check out the video on the front brake.
So there are these three types: vented, drilled, and slotted. Now, almost all brake discs are vented, especially the front. And so you can make a guess already which one is the one that makes a difference. But what about drilled and slotted? Do you think that makes a difference? If so, what kind of difference does it make? Any opinions?
Cooling. On cooling.
On the cooling? Okay. So which one is better, is helping with the cooling? The drilled one? Yeah?
Actually, both of them.
Hmm?
Both of them, but
Both of what? Drilled and slotted?
yeah, but at different rate of cooling.
Mm. Yeah, this guy argues, and I agree with him, the drill is not really helping by much. If anything, you're losing area, right? Think about it. The contact area is less because you drill holes. So I'm losing contact area because of this. And it was originally there because material, you need the material to escape, the brake pad material as it wears out. But nowadays it's no longer relevant. Slotted is also similar, even though there is some help with the, if you think about the slot, if this is the brake disc, if you have a slot there, and this is the pad material, the brake disc is moving this way, okay? The pad is pushing down, and this is a slot. Okay, I'm looking at it from a cross-section point of view. So when the disc rotates and this comes into contact with the pad, so what happens is that the pad will kind of go in a bit, and so you kind of think about like catching the slot. Yes, there is that effect. As a result, your pad also wear out faster. But again, guys, the problem is not the braking force. It's the brake bias control, the braking dynamics and the heat. So your performance, brake performance, contrary to popular belief, it's not about how much friction you get, of course above a certain standard, which most likely is. But brake performance is determined by heat transfer in frequent braking and braking dynamics. And because we're not racing most of the time, for emergency braking, it comes down to this. So assuming your brake is working just fine, and you're not racing, you're not dealing with heat transfer. You're dealing with brake dynamics. I mean, come on. How often are you going to brake from 100 kilometers per hour to 0? 5 times per hour? I don't think so, right? So if you're not doing that, then your emergency braking safety-related issues is here. Safety-related issues or emergency braking, which, for most of us, that's what it comes down to. That's the point of discussion.
The CX-30. We're choosing a model that's equipped with front-wheel drive only. Below it we have a current model Mazda MX-5, which is rear-wheel drive only. A vehicle like a CX-30 will typically have a front brake bias of around 80%, whereas a vehicle like the MX-5 will be around 60% front-wheel brake bias. This means that in the CX-30, only 20% braking force generated goes to the rear, whereas the MX-5 sends 40% braking force to the rear.
And why is that so?
Mass distribution.
Distribution of mass. Okay, rear-wheel drive, front-wheel drive, you guessed it. First of all, there is the axle in the back. You got the differential in the back. And it's just a better distributed weight. That's why I changed from my Acura Integra to Nissan 240SX, because I think it's a perfectly balanced weight distribution. You got the front engine longitudinal, you got the transaxle like right under your shifter, and you got the differential in the back. So perfect. Better handling, much better handling. But for most passenger cars like this, front engine, front transmission, everything in the front. The only thing in the back is probably your fuel tank, that's it. So very, very light in the back and very front heavy.
The reason behind this is that the MX-5 is lower to the ground, which means that it has a lower center of gravity. It also has a stiffer suspension. This means that weight transfer is less pronounced in the MX-5. Being rear-wheel drive, the MX-5 also has less weight over the front tires. We have the engine in the front, but we also have a drive shaft running along the underside of the car and a differential together with drive shafts in the rear. In the CX-30, the weight is not distributed so evenly across the vehicle. The engine, as well as the differential and the drive shafts, are all in the front. So not only does the weight transfer occur easily, there's also no weight available in the front to act on the front tires. The brakes of these vehicles clearly illustrate the different amount of work that the front and rear brakes. Front discs are not just ventilated, they are...
So, cheaper ones, they put solid brake rotors in the back, cheaper, especially for cheaper cars, because you generate much more heat. You can even test it. I mean, after some driving, you hold your wheel, it's hot in the back, in the rear is nothing, right? So how do we achieve this brake bias? Well, we use what is called a proportioning valve. Okay, this is the proportioning valve.
People refer to this valve as a proportioning valve. It is actually called a combination valve. The name comes from its combination of several functions. From the master cylinder, brake fluid travels into the combination valve via 2 ports on the top of the valve. One is for your front brakes and the other is for your rear. Once inside the valve, the fluid for the front system passes through the metering valve.
Okay, so there are several functions of this proportioning valve. One is metering. Second is the proportioning, the brake bias. So before you even distribute between the front and the back, say you want 70-30. Okay, so front, rear. So before you get here, especially for this drum, and this is the situation with most passenger cars. Before you actually distribute 70-30, you actually have a delay. So the metering valve, the intention is to delay braking on the front. The first time you press on the brake pedal, for a tiny fraction of a second, it actually brakes the rear first. And then it distributes the front and rear. So you achieve this with the metering valve. The metering is basically a delay, right? Like a slow flow of the hydraulic.
This holds off pressure on the front brakes, allowing the rear brakes to apply first in a disc drum vehicle.
By the way, you know why you want the rear to brake first?
To prevent understeer.
To prevent, no, why would you have understeer?
The front one brake first.
Okay, but actually if you brake first, if the front one engage together or the same or first, you will actually have the dive, right? You're actually going to dive. And what happens when you dive? The rear lifts. What happens if the rear lifts? It's going to lock. So you'll actually have slippage on the rear first. So you do this first to prevent the dive. Second, the drum actually has a little bit more delay because it has a lot of mechanism and you get the spring and all that. It's just a poor brake. So for this disc situation, sometimes you have the delay, but not much, because there is no inherent delay from the drum. But still, you want the stability. So for light braking, you actually brake the rear first. Brake bias is the same, 50-50, for slow speed braking. Now, when you brake hard, then it starts to dive, and then the front bias still starts to come in. And so first you brake the rear. It gives you stability also. If you ever try to experiment putting the emergency brake, not hard, but just a little bit, you actually get pulled back a bit, and it kind of helps you plant the car. So braking the rear, actually, and this is also the reason why emergency brakes are in the rear, because assuming some loss of steering, rear braking actually is more stable than front braking. Front braking, you dive a lot. Rear braking, it helps you squat a bit. So, so you brake the rear first and 50-50, and then you start giving more to the front as the brake becomes harder.
At a preset pressure, the fluid then travels to the front wheels. This happens through the two ports in the body. If desired, one of these can be plugged and not used. Also inside the valve is a pressure differential valve. This portion of the combination valve is for safety purposes. If pressure is lost on the front or rear, anywhere in the system, this valve will slide, causing the electrode connector to turn the light on the dash, then allow only half the valve to work. This should allow a person to limp their vehicle to a safer place to us.
Well, I don't have that on my old Civic. Okay, let's see. Okay, he gives very good explanation on this.
One of our more common questions that we'll discuss here is going to be the combination valve. A lot of people refer to this particular valve as a proportioning valve. It does have a proportioning valve in it, but that's not actually the technical name. The technical name for it is combination valve. It's a combination valve because it does include multiple functions, which we'll go over here in just a second. The valves are configured and made in two different scenarios. You're going to have one that's going to be for disc drum. You're going to have one that's going to be for disc. They function obviously differently in the car. We'll show you that within the cutaway. Inside the combination valve, we've got a few different components, and again, that's what makes up the combination valve. Within the valve, you've got a metering valve. This is used in a disc drum application. In a disc application, you won't actually have this portion of it. So what this does is a metering valve in a disc drum situation, this actually holds off line pressure really start creating a lot of line pressure, this will actually limit the amount of pressure going to the rear brakes, which will then limit the opportunity and the chance that the car wants to lock up the rear brakes and therefore spin out.
So what you want to prevent is basically locking the rear brakes. You want to lock the front brakes because, like you said, we want some understeer. Actually, understeer is safer than oversteer, and so you actually dive. That's still better than locking the rear brakes. What you control is really the rear pressure. You're not controlling the front pressure and giving it more pressure. You limit the rear pressure and therefore more pressure go to the front. So hydraulics, right? I mean, it goes where it's not restricted.
One of the other questions that we get when it comes to combination,
You have also adjustable proportioning valves if you desire a different brake bias. Say you upgrade your brakes, you upgrade your turbo and all that. So for racing purposes, you have these manually adjusted. Depending on the track, also you might want to adjust your brake bias. Okay. Finally, let's talk about ABS.
Nowadays, an anti-lock braking system is used in almost all modern vehicles. This system prevents accidents like this, where you lose control of the steering as you apply the brakes.
All right. Well, you know what? I want you to do a little bit more active learning on ABS. So why don't you do some research on different types of ABS and the history of ABS. And the systems today. Okay, the sensors related, how it controls. And why don't you start the explanation and then I kind of complete the discussion.
sensors and the four pumps and the four so the four lines. And then there's 3 sensors and 3 lines, which is 2 to the front and 1 to the rear. And for the ABS itself, when the car are going,
So you're saying that the front 2 are controlled independently, but the
Yeah.
rear is only 1? Okay.
so yeah, for the ABS itself, when the car is going at let's say a less frictional road or less contact, normally it will lock up and like that. But with the help of ABS, the ABS have a sensor for, let's take an example for the 4 wheels. So the sensor will detect like the abnormality of speed. So there's like a gear, and the sensor will detect like the.
What does the sensor measure?
Like the teeth of the gear, like how much the rotation is going.
Okay. So what does it measure? The quantity. What is the variable?
The speed.
The speed.
Yeah. So it detects like the abnormality of the speed.
I just want us to practice articulation, right? Because like you cannot say it measured the tooth. The tooth are just pulses. You want to measure the speed. Okay. Yeah.
Okay, so
Continue.
the sensor will measure the speed, and when there's let's say like less friction or slippage, the sensor will detect it and send it to the ECU. And then, because of that, the ECU will release the hydraulics on the brakes
Okay.
to prevent the locking up.
Okay.
And when the car itself finally have a friction, the traction in the traction again, the ECU will continue to will help giving the hydraulics.
Okay. So before we get to the details, who here looked that up? The history of ABS. Okay. You'll do it.
So the history is about aircraft. So when the plane landed, so when they applied brakes, the plane was skidding. So
Yeah.
that's the where the ABS was introduced, and then it was later moved to cars. So
When was that? What year?
1960 something.
Yeah.
Yeah, 1960.
And when does car start having ABS? I think my 1993 Civic had ABS. No,
No,
I don't think so.
it should be around 90.
More like 2000.
More than 2000.
Yeah,
Should
year
around
2000, around late 90s.
Yeah, late 90s.
Maybe late 90s on the luxury cars. And then, yeah. Okay. What is the enabling technology to enable us to have ABS in an affordable way?
So we have like 4 types of ABS, like 4-wheel, 4, 3, 2, and 1. And the major factor is the computational factor. So with the advance in chip design and computing power, it enables us to be cheaper, having more sensor, being more safe.
Yeah.
And this is like one of the most determining factor whether the ABS has 4, 2, or 3 sensor. Most of the car has 3 or 2, the high-end one has high luxury high-end cars has 4, and the it depends on the manufacturer also. So most of the German cars has 4 because some safety standard also depending on countries.
Right.
So this and
it's
yeah.
just more expensive to have 4 actuators, separate actuators. It's not just the processing speed; it's the module for modulating the pressure. Right. You want to add to what your findings are?
First production car like with ABS is in 1978, Mercedes S-Class. It says they developed the ABS system together with Bosch. I think Bosch makes like safety factors or something with automotives also, and they also make like household appliances or
Yeah.
like drill or
Lot of
saw.
things.
Yeah. But in the 1980s to 1990s, the ABS become more available in many more cars,
Right.
rather than just like a high-end luxury car.
Yeah. Now, let's talk about the how the ABS sensor actually signals the need for modulating the brake pressure. Think about the wheel speed sensor, right? It's usually on the CV joints, at the end of the CV joints near the bearing. What you said, right? You got this tooth that, the Hall effect or the inductive sensor actually measures the pulses. Now, okay, so you know the wheel speed, each individual wheel speed, but how will you know you need to modulate or activate ABS?
When the speed, let's say, goes from 50 to when it locks, it goes back to zero, like
zero.
in a instant. So when it does it know to release, actually ABS is pulsating.
Yeah.
It doesn't actually release it slowly, but it pulsates. So it's just like heartbeat. So when it's pulsating one time and it still sees the wheel locking, it will release it a little bit more. Like the pulsation will increase.
The frequency.
The pulsation will increase. So this is how the principle, I guess, of the ABS.
Now, but before it activates, when does it trigger? When will the ABS trigger? So it measures the wheel speed. But locking can occur even though it's not zero, right? I mean, if your ABS only activates once it locks, it's a little bit too late. So how does it know when? Because slipping can occur. Let's say I'm going 100 kilometers per hour. I mean, if you wait for my wheel speed to go down to zero, might not happen. It will slip way before that. Any?
Maybe it has to do something with the brake pressure and the wheel speed.
The brake pressure and the wheel speed.
Like how deep you press on the brake.
How deep you press on the brake? Well, we don't have sensors on that, right? Think about a rolling motion. What is the speed relation with the angular speed? What is the relationship between V and omega? Physics. Come on. V equals omega times What is the velocity here at this point? At the contact point? Ideally. 0, right? 0 means no slippage. And so the distribution of speed is like this. Okay? Along with the radius. Now, what you measure is omega. So, at 100 kilometers per hour, you know what the omega should be, right? V divided by R. This is what it's supposed to be. But, your wheel can slip even though it's going at 80, right? So, if my wheel speed is 80, but I'm supposed to go 100, then I'm slipping. You see? So slip can happen before it locks. And so, ideally, you want to have, in braking, you're talking about 10% to 20% slip. You have to have slip, otherwise you're not braking. So when you brake, the slip starts to increase. But beyond 20% is when you start to actually skid, and the braking friction is no longer optimal. So before, 100% slip, then it's skidding, right? 100% slip means your wheel locks while you're going 100, or while you're going 40 and your wheel lock. Okay, so that's called the slip ratio. And so this is lock. But you want to activate ABS before that. And you want to achieve, so your ABS is not just anti-lock. It's basically tries to optimize your slip to this range. That's when you get the most friction. I don't know whether this video shows that. I think. Well, this talks about the contact point should be 0, right? When the contact point is not 0, when the contact point has a velocity, that means slipping. Okay, so here is the graph for the coefficient of friction with the slip ratio. You want to achieve somewhere between this.
Vehicle even during the braking.
So of course ABS also enables you to steer while braking. That is actually one of the bigger advantage of ABS.
But the big question here is, how does the action of intermittently releasing the brakes reduce the braking distance? To get an answer to this question, we first need to understand how the coefficient of friction between the tire and the road varies with respect to slip. In perfect rolling conditions, the value of the frictional coefficient is nearly 0. However, when the wheel is 100% slipping, sliding friction comes into play. You can expect the frictional values for other levels of slippage to vary like this. But since rubber is a complex material, which has strange behaviors during braking, the frictional coefficient between the tire and the road varies as shown with respect to slippage. It has a peak value at around 12% of slip ratio, and below and above this, the frictional coefficient reduces.
So this is why a locked wheel is not as optimal as a rolling brake, right? It's because the rubber is flexible. If this were a solid wood wheel with no rubber and no pneumatic, then the locking will be the most optimal, right? But this is not, because of the dynamics of the flexing of the rubber.
During braking without ABS, the frictional coefficient which comes into effect is predominantly sliding friction.
So you're here, if you
However,
just lock.
in ABS braking, the clever algorithm adjusts the brake pressure to keep the slip ratio near to 12%, where the frictional value is at the maximum. This significantly reduces the braking distance.
The slip ratio will vary depending on your tire quality and your tire compound.
Now, back to the huge instability issue of the cars. By intelligent electronic braking distribution, which is a subsystem of modern ABS, one can overcome this issue very easily.
Okay, so that's the slip ratio, and the target slip ratio is where your ABS is trying to aim. Okay, I think that should be enough for the day. I give you assignments.
The assignment, I don't have a car.
You don't have a car with you.
Yeah.
Go to your friend's car and do it. I mean, it should not involve any disassembly.
Yeah.
It's just, recognize whether it's. I mean, this is a piece of cake for you. So, but I make the assignment so that it's interactive to the car and it's human in the loop with AI, right? So. So yeah, feel free to use AI, but I want you to be involved in that study. So that's the point of the assignments. And I'm sorry, I'm very late in giving this assignment. So this goes all the way back to week 2. And I give like half a week in between the deadlines, so you can kind of gradually catch up. Okay. Do the post test. Don't forget, do it now. Otherwise you'll forget. Your class is at 11.